All right. Good morning, everybody. Welcome back. Uh, let's get started. So we were in the middle of the lecture and we had to stop after the subtraction discussion. So that's where we begin today. Uh, I hope you were able to access the lecture recordings. Okay, please check them and make sure that you're able to, everything works well, the audio and everything. You may not need the last two recordings, but you never know. Maybe one of the future recordings will be useful for you, right? So we basically ended our discussion in the last class here in this slide where we talked about how subtraction is done for binary numbers. If you have two numbers and you have to subtract a from b, you take the 2's complement of b and add it with a to get a minus b, right? That's the basic idea. Now, I skipped one slide deliberately. I didn't talk about the division then because I thought that discussing the subtraction first will help. Okay, so apparently division in binary is easier than division in decimal. Here is why. When you try to divide a number in decimal system, say imagine you're trying to divide say 37 with 7, right? There are so many sevens will fit within 37, as you can imagine, right? But for binary, there are just two options, 0 or 1. That means a number will either fit within another number or it will not. Okay, so all you have to do is just check whether the number that you are dividing with is bigger or smaller than the one that you are dividing. Okay, so let me show you one example here. And all this discussion is also mentioned here in a longer format for you to read at home. But I think the easier way would be for us to go through this exercise together. So we are trying to divide this number with this one. And basically, this is exactly how we divide in decimal. We start with this number, which is like 4-bit long. Let's start with 4 bits first. Is this number 1001 smaller or bigger than the one that you're dividing with? Smaller. So you cannot really fit this within this number. So you put a 0. If it is smaller, you put 0. If it is bigger, you know what I mean? So that means you have to use one more digit, which is the next one. When you get to that digit, is this number now smaller or bigger than the one that you're dividing with? Bigger. So then you put a 1. And basically, this is the only option. You either have 1 or 0. So you put the number in. And then let me clear it up a little bit. So this is what you're dealing with now. What do you do in decimal system? You basically subtract this one from this one and you get the result here. This is the result. Okay. And you automatically bring down the next digit. Notice this is exactly what we would have done for decimal system. Now the question is this one smaller or bigger than the one that you're dividing with? It's bigger. So you put a 1 here and bring this one down. Okay, and then you subtract out whatever you get, and now you bring the next digit automatically, so you end up getting 110, and you ask yourself, is it smaller or bigger than the one you're dividing with? For this case, it's smaller, so you put a 0 again. Because in other words, can I divide it with the number already without anything else? No, we cannot. So we bring down one more digit, and now you can. So you put in another 1 here, and this is the end. Basically, after that, you have no other digits to bring down. So this is the final result. This is your answer. This is the remainder. That's how you work. Okay. Now, obviously, we can all divide stuff. The thing that I wanted to point to is, what are we doing when trying to divide? We are comparing two numbers. Every time at every stage, we are comparing, is it bigger or smaller? Bigger or smaller? You're basically comparing two numbers. And there is a circuit that we use to compare two things, which is a comparator, as the name suggests. Okay. So apparently, you can use a comparator and compare two binary digits to essentially decide whether to set 0 or 1. And you have to choose between two. Choose 0 or choose 1. When the comparator says it's bigger, choose 0. If it's smaller, choose 1. And that's how you populate. Okay? And can anybody tell me an easy way, I mean, without going through a fancy comparator, an easy way to basically figure out which number between A and B, which one is bigger. And for the interest of time, I'm just gonna give you the answer. Imagine when you take A minus B, subtract one number from the other. If you get a positive result, the first one is bigger. If you get a negative result, the first one is smaller, right? So all you can do is use a subtractor circuit. Folks, are you still with me? Now, let's take a step back. Do you really need a subtractor circuit? I just told you in the last discussion that we don't really have to subtract anything. We have to add. What do we add? We add a number with its two's complement of the other number, and that's how you subtract. So essentially, the circuit that you need is an adder. So we use an adder to subtract. And then we use that subtractor, which is basically deeper down, nothing but an adder, to divide. Because that subtractor, once you subtract two numbers, you look at just one bit, which is the sign bit. If the sign bit shows positive, it's positive. If the sign bit, remember sign bit concept? The leftmost bit is the sign bit. So you just compare the leftmost bit and see whether it's 0 or 1 and figure out which number was bigger or smaller. And you just choose 0 and 1 accordingly. Does that make sense, folks? See, what I'm trying to do here is connect this to something broader, something in the sense of circuit design. And I cannot keep doing it for all the concepts that we'll cover in this course, because then we'll not be able to finish up the syllabus. But at least initially, I will do it more often than usual. Here is why. So that you start trusting the process that, okay, there is something bigger coming in and we are learning things for a reason. You know, there is no other reason for you to learn division at this stage of, technology, because there are 10 different things that you can use to divide binary numbers. You don't have to do it manually, unlike, 50, 60 years ago, for example. But now you still have to know the concept so that when you design the circuit, you know exactly what you need. So do you see that divide could be done with adders? Subtraction could be done with adders. Add could be done. All you need is an adder circuit. So when you go to 433, Introduction to VLSI, the only circuit that you'll be taught is how to design adders. And you'll see like 10, 20 different approaches that people have taken to design adder, optimize adder, make them efficient, make them energy, less energy hungry. Why? Not just, for adding stuff, for doing everything else. A better adder will lead to better everything, better division, better subtraction, you name it. Okay. All right. So moving forward, remember the concept of sign bit. So if you have, say, 4 digits, 0, 0, 0, 1, we reserve the leftmost one to represent the sign, and everything else could represent the actual number. So this is essentially a number, right? Okay. Now, what is the implication of this? We are wasting one digit. It sounds like, okay, it's just one digit. Who cares? I wanted to have this slide to show you how one digit could impact the overall, capability of your hardware. So with 4 digits, you can have 16 different combinations, as you know, right? This is the list. I wanted to have the list here. And with 3 digit, you can have 8 different combinations. So by getting rid of one digit as just the sign bit, you're basically getting from this 16 option to just 8 options. So essentially, in a 4-bit number system, if you use one bit as a sign bit, the other 3 could only give you 8 numbers. You can only have 0 up to 7, that's all. And -7, like that's the cost. But okay, I'm losing a few numbers, sure. That's why I have this other chart I wanted to show you. The higher the bit number goes, the more impact you see in the lost capability. Okay, imagine you have 10-bit numbers. You reserve 1 as a sign bit. So you are left with 9 options, which takes you from 1024 to 512. Okay, so you almost lose half. And then it will keep getting more and more serious as you have more number systems. You must know that we have 32-bit, 64-bit Windows now, right? So just imagine the impact of one sign bit. It's not just, hey, just losing one bit. It is losing a significant amount of storage capability. But we have to do it because we need signs. We need to distinguish between positive and negative numbers. Okay. Does that make sense, folks? And the reason for pointing this out is to show you a decision that the architecture folks make. How do you represent negative numbers? Here is how. Reserve a bit for sign. That decision could lead to your 1024 gigabyte storage being only able to store 512. Everything else is like not usable. All right. Now, moving to the next slide. If it seems like I'm trying to fast forward, it's because I am, but don't feel like you have to just cope up with it. If you feel like, hey, I want to listen to it again, you're going too fast, please stop me. I'm more than happy to go back and revisit. Okay, so binary codes. It's another concept. We basically revised how to convert binary numbers to something else, decimal numbers to binary, and so on. Any number system to some other number system. But turns out there is an approach that we often use, which doesn't require a direct conversion from decimal to binary. So long story short, you can read it at home. These are for you to read it at home so that you don't have to read multiple pages of the textbook. Okay, you are welcome to do so, and I highly recommend that. But in case you are short on time, at least make sure to read whatever is in the slide. Okay, every slide that you see, will see throughout the course, has been custom made. All right, because I spend the time to decide which one is necessary for you to see. Okay, so this is a decimal number. I could either, when I try to convert this to binary, I could go through the binary conversion process. But people figured out a smarter way to just quickly do it without going through that conversion algorithm. Represent every digit with binary, its corresponding binary. And that makes it super simple. All you have to do is have 0 up to 9. Representation for 0 to 9. That's the 10 digits that we have in our daily number system, decimal number system. And represent that quickly. And at some point, you can memorize that, right? You see my point? 0010 is what? 2. 0011 is 3. So basically, wherever you see 3, just represent 0011, and so on. So all you do is you take every digit from the decimal system and represent that with the 4-bit binary. That's it. And this coding system is called BCD, binary coded decimal. There is another name that is often used. It's called 8421 BCD. Why 8421? Notice 1 represent 2 power 0, 2 represent 2 power 1, 4 represent 2 power 2, and 8 represent 2 power 3. So basically, if I were to convert a decimal to binary, remember that like we had to use the base power position, right? And that's why that's what it represents. But I think this is the most widely used term, BCD, binary coded decimal. It makes it easier for us to map it into hardware. If you think about a 7-segment display, how many of you have seen a 7-segment display? Okay. You see that in a calculator, for example, right? It doesn't have very high resolution, but it has 7 segments, and you can use those 7 segments to show any numbers, any digits, even some letters as well of the alphabet. So it's easier to control those 7 bits using BCD coding sometimes. We'll see that at some point. Okay, but remember, this is just one code, which is very common. But there are many other binary codes that people often use for different purposes to represent decimal numbers. Okay, and this is a chart from the textbook. Obviously, this is not a conclusive list. There are many other coding algorithms and coding approaches that people have used and have been using and coming up with, especially in the age of cryptography. This binary coding and other kind of coding is necessary. And I'll give you like just a couple of examples without going through the laundry list. Don't worry, you don't have to memorize anything. If you are wondering, hey, do we need to learn how to do XYZ? I will tell you if you need to memorize anything, all right? So this is the BCD coding system that I told you. This is 0 to 9 digit for decimal. Take a look at, say, 2 out of 5 code. This is interesting. Why? So in this coding system, you use 5 bits every time. There are like 5 bits. And 2 of them will be 1. So that's why the name, 2 out of 5. Notice this. Look at all the numbers. There are exactly 2 1s in different positions. Okay, and everything else is 0. So there is an asymmetry, more zeros than 1s. 2 0, 3021s. And depending on the position of these ones, you could represent 0, 1, 2, 3, 5, whatever. So these are unique, obviously. For example, this is a unique code for 4, but this is not a direct conversion of 4 to binary, is it? It is not. It is just a code that people came up with using 2 ones and 3 zeros. So apparently you need 5 digits to achieve that. What is the advantage? So this particular coding system, notice you always have 2 ones, right? If for some reason you have a mistake made, either through hardware error or something like, you know, I don't know if you know about this radiation strike. Once in a while, when you have high radiation coming from the solar storm, it messes up our electronics and it kind of flips many of the bits, 0 to 1, 1 to 0. And there is only one way to notice that something changed accidentally. I didn't want to change it, but it got changed because of environmental reason. And that is basically, you compare parity. Parity meaning like how many ones, how many zeros, and something like that. So if for some reason you end up with more ones than 2, there is something wrong. Or you see my point here, right? And that's obviously there is a possibility that one of these will become 1, the other one will become 0. So you are left with 2 ones essentially, but the chances of that happening is fairly low. Okay, so they use this coding approach as more like something that is less error prone. It is self-checking. And we use a parity circuit to check whether there are 2 ones. If there is, instead of 2 ones, if there is 1 or just 3, then we know there is an error. So you correct that portion somehow, or discard that portion, disregard that portion. If there is no error correction available, just disregard that portion, that it's invalid. And it happens all the time, by the way, not just for, radiation strike. There are many other reasons why mistake can happen. Okay, one other example is a gray code. Notice this is another interesting coding approach. 0 is represented by 0, 0, 0, 0, looks fine. 1 represented by 0, 0, 0, 1. But 2, what should 2 ideally be if I were to just convert it to binary? 0, 0, 1, 0. But notice it is represented as 0, 0, 1, 1. Why is that? So in this coding approach, their strategy, it still needs 4 digits only, which is good. You don't have an extra digit for no reason. In this representation system, they change just 1 bit at a time, just 1 bit. That's the rule. So notice if I were to go from 0, 0, 0, 1 to, let me write it here, 0, 0, 1, 0, which is the binary representation, the next binary representation. Notice this bit will change and this bit will change. So you change 2 bits at a time. If you go from 0001 to 0010, you have to change 2 bits at a time. Does that make sense, folks? But instead of doing that, if you go from here to there, you just change 1 bit. And if you compare between any 2 adjacent digits, you'll see just 1 bit change will occur at a time. This is called gray coding. And this is deliberate because, oftentimes when you try to achieve better sensitivity with between neighboring options, if there is just 1 bit change, that is often faster and more sensitive. Does that make sense? So oftentimes when you try to represent an analog input, an analog change with its corresponding decimal binary, gray coding is a good option. Does that make sense? So you can also come up with your own coding approach. Sometimes people have to go beyond 4 bits, as you see here, to 5, 6, 7. If you could justify a unique advantage of using 7 bits to represent these digits, sure, people will buy that. But without justifying something unique, we typically try to keep the bit count as small as possible. Remember, you have to store them somewhere. There is a memory block, and every bit will require its own memory. So that's why the smaller the better. Are you still with me? Okay, don't give up. Okay, ASCII code. You know this already. It's a very quick slide to talk about it. People came up with a way to represent our letters in the alphabet with a unique set of codes, and that's called ASCII code, and American Standard Code for Information Interchange. It is a 7-bit code. So basically there is a chart that people follow. They started following it like decades ago, and they still do. I basically use this example in the first lecture, remember, about cat and bat, as to how there could be 1 bit difference between ASCII codes that could change a letter. So you guys all know about ASCII code, right? Okay, just as a reminder. All right, let's move to something that connects our Boolean concepts to circuit design now, gradually. So now we'll start looking at how Boolean function could be derived, looking at a schematic. And please refer to a slide that I showed you where we had AND gate, OR gate, NAND gate, NOR gate, inverter, buffer spelled out with the truth table as well as the symbol, circuit symbol. These symbols are pretty standard. And just to help you quickly remember, this is an AND gate. And if you see a circle in front of it, it represents NAND. So typically we represent inversion with this extra circle. So for example, this triangle represents a buffer. A buffer is something that doesn't change the input. Whatever input you get, whatever input you give, you get the same output. So A gives you A. That's a buffer. You might be wondering, why would we need that circuit? Introduction to VLSI 433. It's typically used for signal restoration. All right. Anyways, so inverter will do what the name suggests. It will invert. If you provide 0, you'll get 1. If you provide 1, you'll get 0. Why would you use it? For everything, but the very easiest example would be whatever we learned. 1's complement. If you just want to take 1's complement, take an inverter, and that will do it. Anyways, so see the difference? Whatever inverts, you have, whenever you need to have inversion, you add a circle. So this is an OR gate symbol. And when you connect a circle with it, that becomes a NOR gate symbol. Okay. And depending on how many inputs you're dealing with, you can have 2 inputs like this, input 1, input 2, or more, or input 3, right? That's the pretty standard concept. Okay, now having that in mind, let's try to make sense of this circuit. We'll do some easy exercise first, and then we'll do something together. So notice this is an inverter. You have an input B, so the output will be B prime. And this is A. What kind of gate is it? For your easy recognition, the textbooks also provided this dot and plus symbol, but it will not be provided in real life, by the way, or in your exam, just for the sake of it. So this is an AND gate. What AND does is basically takes these 2 inputs and multiplies. It's not really multiplication, it's AND relation in Boolean, right? So you get A, B, bar. And then in this gate, which is an OR gate, you have another input C. So this is one input, this is the other input. The OR will basically take, obviously will be represented as plus, but it is not really addition, it is OR. So that's what you come up with. This is your final logic function, Boolean function. Okay. Well, here every stage is given, but in your exam or in your homework, for example, none of this will be given. All you will have, let me just clear this up for now, for practice. Okay, let's do it. So this is what you will have, only the inputs. You'll have only the inputs and we'll work on the output together. So what type of gate is it? Let's do it quickly, all right? OR, yes, so you have C and D. The OR will basically give you C plus D, right? Simple, all right. If you have A here, this is an AND gate. What AND will do is take both inputs and give you the product. So you have C plus D times A. So you'll have C plus D and A. It doesn't matter whether you do A and C plus D. Basically, they're interchangeable. You'll see some rules that we have. Okay, and then this is an inverter. So it will take whatever you have, C plus D times A, and invert it, invert the whole thing. What about this one? This is B and E. This is an AND gate. You'll be getting BE. And then finally, at the OR stage, both of these will be added. That's all. Super simple. Does that make sense? Don't worry, you'll get to practice a lot more in your homework and you should be in good shape. Let's do one last practice with this circuit. Ready? Let's do it together very quickly. So this is an AND. You have two inputs, C and D. What should be here? C, D. Yes, thank you. And it doesn't matter if you do DC, it's the same. Okay, and then A and CD both are inputs for the OR gate. So you end up getting CD plus A, yes, or A plus CD. I'm gonna do it this way, alphabetically, A plus CD. And then after the inverter, you should get A plus CD prime. Thank you. And this one, let's do this branch as well. BE, this is an AND gate, so you'll get BE. Yes, so you have an input BE, you have another input, which is this one. All you have to do is basically add this up, A plus CD prime plus BE. And just a reminder, this plus is not really an add, it's an OR. So that's your logic function. Simple. So given a circuit, you could see, this is interesting. You don't, I mean, when I was like you, I had no idea that this could be so impactful. What we are doing right now, right here, is called reverse engineering. You're looking at a circuit topology and you're figuring out what kind of logic it is implementing. So imagine, and that's a big concern for many hardware designers, like Intel, Samsung, you name it. People can look at a hardware design and there are automated algorithms for it that takes images of the chip and tries to make sense of what kind of gates are implemented, and it reverse engineers the logic and tries to figure out, or figure out the Boolean logic underneath. And often it can break cryptography. It could be used to steal information, you name it. Okay, so that's a big concern. Yes. Oh yeah, that's a great question. This represents the function, Boolean function. Typically we always use f because it stands for function. Sometimes you'll see in some textbooks lowercase f, sometimes uppercase, it doesn't matter. You could use other things like q, doesn't matter, but typically it's like textbook standard to use it. All right. So this function, this circuit represents this logic function. And don't worry, something's coming up. We'll learn how to convert a real life scenario to a circuit like this. Okay. And that's when things will make a lot more sense. Okay. So you see that we just did reverse engineering. And just as a quick tangent, just to avoid reverse engineering, people often incorporate dummy gates. Like they add more gates than there is the need for. And they have to insert it in a way that it doesn't change the logic function, but it confuses the reverse engineers. Okay, so that you cannot figure out and copy whatever Intel is making or whatever Samsung is making. And more importantly, it's honestly not really for their business purposes. It's mostly for defense. So imagine if one of the drones from one of the countries falls in another country in a hostile territory, and they takes that and reverse engineers and figure out the weakness, and that's when they could attack it. They don't necessarily, they have their own drones. They don't have to just steal the drone information. They have to find a way to detect or destroy the drones remotely or something like that. So that's the concern. For most defense purposes, they use, yes. Oh, sure. Okay. So I was going to say that for many defense hardware design, people often use a technique called camouflaging. And that's exactly what I told you. So hardware camouflaging, they use extra logic gates here and there that will make it. What if there were like more gates and it's going all around and you don't really, it doesn't really make sense. You end up with a function that is not really the function that was being implemented. You have to do it in an intelligent way. What's the catch? Remember, everything has a cost. If you have an extra OR gate that takes an extra area, that means your chip area is limited. You lose some functionality. If you have dummy stuffs that are useless, you lose space for useful stuff. So you make a call. We want security. We want to make sure even if it falls in the wrong hand, they cannot reverse engineer it. So they make that call. But you would not make that call for an iPhone because you see, like you cannot sacrifice performance. So if somebody tries to reverse engineer, how do you handle it? Sometimes people go to the depths where if you try to open certain parts, it will destroy itself. Something like chemically. It will not just burst out, right? But it will chemically destroy itself. I mean, it will go with the casing or something like that. So there are other ways people do it. Yes. Yes, exactly. These designs. But as you can imagine, if you remember the numbers, if not, please go to my lecture 0, and these numbers are there. There are 2 slides where I showed Intel, uh, you know, processor and AMD processor side by side. Just look at the number of gates. Number of transistors in billions. Number of gates will be in hundreds of millions. So instead of 5 gates, you'll have millions of gates connected with each other. You cannot do it manually. And obviously, you're not going to reverse engineer it manually, as you can imagine. Not in today's technology. At some point in 1971, when the first microprocessor was introduced, people used to hand design this stuff. And I've seen that personally. It's in Intel's museum. They used to draw this using pencil and ruler. Like literally, engineers used to draw this like they sketch the buildings. Used to sketch. Now they don't do that anymore, obviously. There are automated design tools. And if you're curious, 651 is, look at ECE 651, which is taught here, and I will be teaching it next spring. Obviously, you cannot take it at this stage, but but I'm just going to tell you that there are answers to all these questions. These are not unknown to us, and people learn this gradually. That's the end. That's called computer-aided design of VLSI systems. So that's when you hand it over to the computer. Okay, but you are the brain behind everything. You have to know everything. You have to design everything. You have to design in a small scale, and then ask the computer to take it and like basically explode, like make it into billion level or trillion level. It will learn from your design and just take it to the highest scale possible. But you still have to be the brain behind it. Okay. All right. Let's move to the next slide. Let's try to do the opposite now. Let's try to come up with the schematic from this function. This is a Boolean function. I could represent it to f. Okay. And then I'm going to draw a circuit for it. Folks, notice how many, is this an AND operation or operation when you have product? And how many variables are you dealing with? 4. Remember one thing, A and A prime, they're basically called literals. A variable and its invert are often treated as just one variable, honestly, because you can just use an inverter, which is the cheapest, easiest possible circuit to get the other. And on chip, when you design chip, you have an input A, you can have an inverter and take and share the output A prime, A prime, A prime, and distribute it across wherever you want. Does that make sense, folks? Just like taking a connection out of a wire in multiple direction. So we assume that A and A prime are available at any time, at any moment you want. So basically, they're often called literal. We don't typically treat them as separate inputs. If I ask you how many inputs I have, yeah, if you tell me 1, I don't mind. So you often call, we have 1 literal or something like that. Anyways, so there are 4 variables here, A, B, C, D. What I'm going to do is I will use an AND gate. And I will be doing A prime, B, C prime, D. Okay, but for the sake of it, I could also show that I get A prime out of A. I can also show the inverter. I can also show C prime coming out of C if I want to. Okay, I mean, just to be thorough, let's do it. But trust me, we don't create C prime and A prime every time before every circuit. We just create them once and then we share it across everybody. Okay, that's why oftentimes in upper level textbooks, it will not be shown this way. It will be just C prime. We just take it for granted. Okay, now, so what do you get here? You get A prime, B, C prime, D. And then you need the next term as well, AB. It is easier to do it this way. Implement the product terms individually, and then you sum them together using an OR gate. Okay, so AB, you create another AND gate with A and B, and this is where you get AB. You need B prime CD. Sure, let's do it. I mean, I'm running out of space, but it's fine. I'm gonna make it really small here. B prime C D, and you can see that you can create B prime with an inverter. And then finally D prime. Okay, I don't need a gate to create D prime. It is an input by itself. Does that make sense, folks? So I'm gonna Oh, sorry. I'm going to use an OR gate. And how many inputs do I need? Notice 1, 2, 3, and 4. Does that make sense, folks? I need 4 inputs. So one of them will come from here. The other one will come from here. And the third one will come from here. And the fourth one will be D prime, which can come from D if I try to be that detailed, like D to D prime, and then that's your output. And this is the function that we try to implement. Is it difficult? No. And by the way, things that are impactful doesn't have to be difficult, honestly. So digital electronics is so impactful that it is ubiquitous everywhere, but it's not, honestly, in my opinion, that difficult. So any kind of reservation that people might have, oh, this field is not for me, is not rightly placed. So it's definitely manageable for all of us. It's really that simple. I'm not making it up. Okay. And don't worry, we'll practice more. I don't want to spend time too much in the class practicing, but you can use your homework assignments to practice more. All right. One other quick example of how truth tables are made is we can look at a circuit and then create a truth table for that circuit. And one approach is just look at how many inputs you have in the circuit. 2, A and B, and this is your output. These are 2 original inputs. So your truth table will have 2 columns. And with 2 variables, you have 4 possible combinations. Right? Now, if I somehow add one more input to this C, this is not the truth table you need. You need a truth table with A, B, and C, and you have 0, 0, 0, 0, 0, 1, blah, 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 blah. Total 8 combinations, as you can see, ending in 1, 1, 1. Make sense? So basically, your circuit determines the size of the truth table. And then one way you could do it is put in this row here. So A equals 0 will give you 1 because this is an inverter. B equals 0. So you have 0 here. This is an OR gate. Just you have to remember the OR, AND, and invert. These are the foundational and fundamental logic. It's almost like you have to memorize it. It's not memorization. It's essentially real logic, human logic, right? So when you have 1 and 0 and you're doing OR, as long as you have just one somewhere, the output is 1. Simple. So that's what you get as an output. So you plug in every one of these inputs in the circuit and you see the output and you fill the third output column. That's how you can populate or generate a truth table. Make sense, folks? Okay. You might be wondering, hey, who does it? Like, I mean, I could have just, figured out the function. Yes, that's true. One of the reasons why people might want to do it, plugging into the circuit, is the circuit could be really complicated. And you don't really want to express that in a functionally representable format. Think of reverse engineering, right? You are trying to reverse engineer. Think like a reverse engineer who just got hold of hardware that they try to steal now. All they will look for is how many inputs you have. Sorry. Say they have 27 inputs. Are you still with me, folks? They have, say, 27 inputs. That means you need a truth table with 27 input variables. Just imagine how many rows will be there. Can anybody guess? How many rows you have with two inputs? 2 raised to 2. How many rows do you have with 3 inputs? 8, meaning 2 raised to 3. So how many inputs will you have? How many rows will you have with 2 raised to 27? Is that a small number? Just try to put it in MATLAB or even Google it. Like, what is 2 raised to 27? Like, this is crazy. It's crazy big number. All right. So anyways, notice what I did. I put in 0 and 0 in the circuit and I let it trickle through the circuit and find the final output. That way I can get the truth table. But if you have too many rows, that's not an easy thing to do. It's going to take a long time. So you can use a supercomputer. You can use a supercomputer, which can take months to finish up all this. And in certain cases, it will never be able to finish up because the time required will be, insane. Does that make sense? Like 100 years. It will take 100 years for. That's where the quantum computer comes in. It can break in a few seconds, but it's fine. I'm not gonna get in there. But do you see that there is a number game associated with it? So you could do reverse engineering. Here is how. You could just keep plugging in these numbers, identify the inputs, put in all the combinations, see how the output behaves in the hardware testing phase. Okay? And hardware, don't give up. Are you still with me? Okay. How many outputs do you have? Tell me. One. Just one output. So probe, it's like people have probe stations where they can connect different probes and measure the voltage at different nodes of the circuit. So just connect one probe at the output and notice how many inputs you have. Probe those inputs. If you have 10 inputs, 10 probes, 7 inputs, 7 probes. And you keep providing 0, 0, 0, 0, 0, 1 in the inputs. Make sure you go through the row, all the combinations, and you just measure the output. Interestingly, the output could only give you 0 or 1, 0 or 1. You just measure the output and you populate this truth table. And I will show you in the next lecture, given a truth table, you can figure out the function. So you don't have to do what we did here. Remember, not here, here. What we did here, go through every stage, go through every stage. No. You can directly generate the final output given the truth table. Are you still with me? So creating the truth table is the first thing that a reverse engineer will try to do. And how do they do it? Imagine you throw a Core i7 processor somewhere and somebody gets hold of it. They smuggle it to a company that's trying to steal the secret that Intel spent years developing. They'll probe it with their probe station, provide inputs, take the output. It will take months because there are so many combinations, and they will create a truth table. They'll reverse engineer. Once you get the function, notice, once you get the function, you don't even have to go through and recognize the circuits individually. You can generate the function and design the circuit backwards. That's exactly what we did. Remember, give me 1 second. That's exactly what we did here, didn't we? We knew the function and we could design the circuit. That means you design the processor. You basically steal the design of the processor, right? What saves them is the humongous number, honestly. So it will take a company several years, 4, 5, 7, I mean, depending on the complexity, years to finish reverse engineering something. So that's why by then they will move on to a better hardware and there's less motivation. But still, there is a risk. They don't have to reverse engineer everything. Maybe they just try to reverse engineer one functionality, right? How does Apple do finger recognition? Something like that. If they could reverse engineer that portion, there you go, right? Certain features. Okay, so moving to the next one. You know that Apple has a dedicated chip. It's not, done over software. They have a dedicated chip to test your fingerprint. Do you know that? Or they advertise it quite heavily, right? For example, if you use Apple keyboard, which is not wired connected, it can recognize your finger. Like they basically store it there. It's not sent to Apple's server. Okay, it's stored in hardware. So just imagine if you take that portion that deals with recognizing, it's a much smaller problem set. It's not a generic processor, which has like millions and billions of gates. It's a small processor relatively, whose only function is to recognize how to, determine, and it does it very well. So if a company who is just getting started wants to get ahead of Apple, they first reverse engineer that portion, try to reverse engineer that portion, and then you see my point here. I'm not trying to encourage reverse engineering here. I'm trying to show you what the engineers have to deal with and have to be mindful when they design it. So that you have to take countermeasures so that your years of investment doesn't go in the wrong hands. Okay, one other easy testing. This is the last slide that we'll cover today. We don't have much left. It's okay. We'll get it done. Okay, so equivalent expressions. So Boolean algebra, for example, this one is a Boolean expression. And this is another expression which doesn't look anything similar to the one on the right, but turns out they're equivalent. So given an option, we would rather use these to implement the circuit than the other one. Why? I'll show you in the next lecture. You will see the more complex the function looks like, the more components you'll need to design the circuit. And remember, every component will take up space, and space is money, right? On a chip, you try to minimize the space as much as possible. Area optimization is one of the biggest things that we need to do. Why do you think we try to make the transistor so small, so that they're smaller than virus and bacteria? Because we need to fit more. And if you're wasting random gates here and there, you're not really doing them any favor, right? So you have to optimize this Boolean function to make a smaller representation. The smaller, the better. The easier, the better. So, but they have to make sure that they're equivalent. They're representing the same logic. And how do we know something is equivalent to something else? Looking at the truth table, okay? So look at the truth table for A plus C and B prime plus C, which is this column. And AB bar plus C, which is this one. Just compare these two columns. You'll see they're exactly equivalent. Exactly the same. So I can tell you that this function equals this function. But obviously, I'm not going to do it this way, am I? Because how many functions can I check? How many functions? How do I know that this is the function which will magically fit the other function? Right? The brute force will not do. But I'm telling you, after you somehow calculate and reduce this expression on the right down to the expression on the left, which we will learn about gradually, how do you know that you got the right answer? In your exam, when you're doing it, how do you know? Did I make a mistake? So you arrive at this conclusion. How do you know that your answer is correct? An easy way to do would be to check the truth table and see whether they match. By the way, in your exam, you don't have the time to check the entire truth table. Just take some random picks like 0, 1, 1 and see whether both of them give you the real result. 1, 1, 1. See both of them give you the real result. Am I making sense? But in practice, yes, if a computer was doing it, it would check the entire truth table to make sure they're compliant. So once you optimize the hardware, there is a verification stage where they verify and make sure the truth table match after and before optimization. Okay. All right. That's where we stop. And thank you for it. We'll resume here in the next class.